Okay, so we're off and running. Right, so I've given you a heap of stuff here. Let's just run through that in some sort of order. One thing I haven't given you hasn't come out, but that's all right. First of all, past exam papers. So there's May 14, November 14, May 15 it should be, and November 15. Keeping in mind there's no time zone 1 or time zone 2 for paper 3 for mathematics. In other words, in May, don't get 2 exams, you only get 1. So because it's 2020, you get 14, 15, 16, 17, 18, 19 times 2 plus a 1, you're going to have 11 exams to study, which is more than any other year level has had to study. And that's a huge advantage. It's a massive, because by doing all of these exams, you would have covered most of the questions they could ever ask. So you're really, really lucky in a lot of ways. Yeah, including some of the more less examined stuff like Taylor series and that comes up in these in the last few years. So please, can you have a look at that? Oh, there's the last question. I remember you doing that on your test for. Do you remember doing that question? So you've already seen some of these. That's the first piece of information. The next piece of information is, of course, I normally have a test on chapters 1 to 3, but we're not going to have a test. We're going to push through and just have a test at the end of this unit. Probably 2 tests, yeah? A practice one, and then maybe you can actually have a real one. How does that sound, yeah? So, that said though, I'm just wondering, maybe you should hand this in as an assignment to me on Friday, okay?
Friday?
Yeah.
Tomorrow.
Oh, okay, let's make it Monday then, yeah? Can you hand that to me on Monday?
Okay.
Okay, just as a practice test. I haven't given you the answers to that. However, what I have given you is the revision. The revision I normally do for this chapter that's the revision I do. So I prepare a little revision handout and there's the solutions to that revision handout. I hope that's not to the revision, I hope that's not the answers to the test. I don't think it is, but so there's that. Okay, so you've got some revision for that to do as well, plus this. I'd like that on Monday. Let's say Monday, could you hand that in to me? Now, of course, during that time, it's not a bad idea, maybe, Vincent, to do 1 or 2 problems on this, keeping in mind you can't do everything yet, but you should be able to do most of those in preparation. So maybe late next week we can do a practice exam, and then the week after we can actually do an exam, and then we'll stop for the rest of this term. And we'll just go for IAs and EEs every single class, okay? So let's do that. Now, I've given you some information. Years and years ago, many years ago, when I first started teaching this, I only had 1 or 2 of the new exams. In other words, back in 2015 when I was teaching this, I only had 2 exams from 2014. So what I had to do was go back in the past and use some of the ones prior to 2014. Now, these exams contain material you don't really need anymore, but still the majority of the material was useful. They were much harder questions too. You go back in the previous years, the calculus option was, wow, really hard. So students often do go back and look at some of these. Do I think you need to? Well, I've given you this information plus solutions just in case you want to. I probably wouldn't at this stage. Yeah? Maybe you can look at some of this stuff later if you have time, but I think I've given you enough work to do. It's better to look at just the 2014 onwards. Yeah. However, if you wanted to go and just flick through a couple of questions and look at some stuff in here that looks like you should be able to do it, especially some of the differential equations questions, by all means there's some extra practice there as well. Okay, but probably put that at the back. I think you've got enough to do there. Okay, so that's the work. Okay, let's see if we can remember all of the tests. Nathan, let's run through these series tests, yeah? Just every class I want to do this. So, series test. By the way, I think I've got to finish this at 5 minutes to 12 o'clock because I've got math studies after this. What's the time? How long have we got? 11:25, yeah, so we've got about 40 minutes. Oh, have we? Yes. No, we've got 30 minutes. That's okay, we can do it. Okay, Nathan, you ready? Let's run through the tests. Test 1, what do we do? Diverging test. What's the diverging test say? Can you remember? Diverging test says what? The infinitieth term, the term at infinity, if it's not 0, then it's diverging. So this one's easy. This is just the limit as k approaches to infinity of uk. If that doesn't equal to 0, then I know that my sum will diverge. Hey, how about if it does equal to 0? What does that mean? Absolutely nothing, really. It means it either could converge or diverge, which doesn't really tell us anything. Yeah, what are you doing, Rubby? Yeah, rub your head. It's a bit... Okay. I don't have a problem with it, but I'm just wondering what you're doing there for a sec. Okay, so that's a divergent test. 2, what's the second test? Comparison test, yeah. What are the 2 things, Diana, that you would compare to for the comparison test? What are the 2 most common comparisons we make, everyone? One is to a geometric. Yeah, a geometric where r is going to be less than 1. Why? Because we know that convergent. Yeah, so if you can compare to a geometric series that you know the common ratio is less than 1, then we can compare. What's another common comparison? P-test, well done. Yeah, so we're going to go to my p-test. 1 on x to the power of p. Yeah? Remember this, if p is equal to 1, what? P is equal to 1, it diverges. Yeah? If p is equal to, if p is less than 1. If p is greater than 1. Converge. Okay, so that's our p-test that we can regularly refer to. That assumes you can make a comparison. What if you can't make a direct comparison? What do you need to use? Yeah. So if we cannot make a direct comparison, in other words, if you cannot form an inequality like this, if you can't form an inequality, say, here's a classic one where you might have how about this k squared plus 1, yeah, which is less than the sum of k squared. Do you agree with that? Yeah, I can make an easy comparison, can't I? I can make a really easy comparison to this one here. Here's a situation where I can't make an easy comparison. In other words, this is not true. Yeah? In other words, this one's greater than that. What happens in that case? Yet I still know this one is going to converge, but I can't make an easy comparison. What do I need to use? I need to use my limit comparison test. So this is 3, where we use my limit. Use my limit comparison test. What's my limit comparison test say? Limit as k approaches to infinity of ak divided by bk has to be equal to L, which has got to be greater than 0. What we're saying is, at infinity, the terms, if one series, is approaching, is converging, then because the ratio of the 2 series is fixed, the other one will also converge. So if you can produce one that converges, then this one here will converge. If you can produce one that diverges, then this one here will diverge.
What if L is less than 0?
Well, it's negative then, isn't it? And then you got one series positive and one series negative, you can't compare. Okay, you can't do it. I think that's what they're saying. Okay. Good, okay. Next test, what's the 4th test? 4th test is the integral test. When do you think you'll use the integral test? In fact, what is the integral test? The integral test basically says if you do the improper integral and the improper integral converges, then what? It converges, So when would you use the integral test? Well, you might use the integral test when you can clearly see, maybe something like this. You've got the sum of, say, how about this? You might have ln k divided by k. Or something like that. Yeah? Agreed? Or you might have something like this, the sum of, how about this, x squared sine x cubed, or something like that. Not x, it would be k. You might have something like that. Straight away you can see what rule would I use to integrate that. I'd use the substitution rule, wouldn't I? When you can see it's very hard to form a comparison with either a geometric series or a p-test, if it's hard to form or see that, then the next thing is you're probably going to have to do an integral test. Yeah? But you'll be able to see the integral test because Vincent, you know how to integrate stuff, yeah, and you can see whether it's a substitution rule, yeah, you can see whether it's by parts. So straight away you say to yourself, I've got to integrate that, or if it's a readily integratable thing. So what does the integral test do? Well, it means that if I form this into a function in x, if I make f of x equal to x squared sine x cubed, for instance, yeah, and I find the integral from 1 to infinity of f of x dx, yeah, if this converges, what does that say about this? It converges. If this diverges, then that diverges. So the integral test is really cool. Now, the integral test is responsible for the comparison test, isn't it? Why? Why is the integral test related to the comparison test? Yeah, this integral test, that integral test here, was fundamental in formulating the p-test. That's where the p-test comes from, doesn't it? The p-test comes from essentially the integral test, which we did back in chapter 2, and also is in your book in chapter 3. So in your textbook, they've done that twice. Yeah? Okay, today I want to move on to a new test, and this new test is going to be our 5th test. It's going to comprise of probably a couple of tests. It's called the alternating series test. And if I could get this done today, I would be happy, but I'd like to get this done and possibly another test called the ratio test this afternoon. If we could meet again at 2:30, can we? Great. 2:30 to 3:30, please. We could probably get all of this done. Now, inside of here though, inside of this test here, there's kind of 2 tests. One is what's called the conditionally convergent test, and the other is called the absolute convergent test. But do you know what I might do? I might call that a 6th test. Yeah? The 6th test is what I call conditionally convergent. Conditionally convergent. Yeah? And absolute convergent. The absolute convergent test. Now, the textbook really puts this in here as a subset, really, of the alternating series test. But I think you're best off thinking about it separately. And the last test we have to do, we could probably get this done today, everyone, perhaps, is the ratio test. Yay. Ratio test. And then we're finished. And then we've got 1 chapter to go. So, is that cool? Let's rub this off. I might not summarise all this again until we're finished. Okay? When we finish, we'll summarise it again. And then we'll summarise it again and again until it's so clear in your head that you know when and how to use it, because this is really quite tricky. When to use it. Yeah? Now, I've included some great examples here from past exam papers. You'll notice the first part of your test is basically, well, which test do I use to show convergence or divergence? Yeah. Okay? So there's some clear ones that hopefully you'll be able to see. I won't tell you that. I'd like you to explore that yourself and discover that yourself, because that's important. Guess what? In the exam, there's about a 50%, 60, possibly even 70% chance they're going to tell you what test to use. Which kind of takes all the fun out of doing a really good job of teaching it, doesn't it? Really. I'm teaching you this so you don't need to get help, but sometimes they do tell you that. Let's not spend any more time. Let's look at this alternating series test. I'm going to clean the board. Don't worry, I'll write this down again for you for sure. Yeah, we'll summarise it until it's so ingrained in your memory that you'll remember it when you're 50 years old, probably. Maybe. If I made it into a song, you'd never forget it, but we won't do that. So let's do this alternating series test. The alternating series test. Right, I just better get a bit of a reference to my textbook. Okay, so they talk about an alternating series test by looking first of all. So I'm going to start with this. 1 to infinity of 1 divided by k. Yep. What's that series? Converge or diverge? Diverge. Why? P-test, good. And this is 1 plus a half plus a third plus ... What I'm going to do is I'm going to change this and I'm going to put in what's called a sign generator. Yeah? And I'll do that by doing this. So we know this one here diverges. We know that one diverges. But if we do this, yeah, if we do this, hopefully you can see that this here is what we call a sign, well I call it a sign generator, I don't know if anyone else does. I call that a sign generator. Why? Because it generates the sign. In other words, when k is 1, what's my first term? Positive or negative? Yeah, it'll be positive, won't it? My second term will be? Yeah, third term, positive, and so on and so on. So basically we end up with, this is 1 minus a half, plus a third, minus a quarter, plus a fifth, yeah, ... Okay, we call this an alternating series. Why alternating? Because it's going positive, negative, yeah? So I call this thing here, I call this a sign generator. So if I say that, that's really what I mean. Can someone think of another fancy sign generator? Using sine and cos. We could use cos, couldn't we? Remember cos is 1, then cos is -1. That fly's been in here for days, isn't it? Yeah? So we could use another sign generator like this. We could go cos, yeah? How about if I went cos k minus 1, I'll do those. Cos k minus 1 times by pi. Will that work? In other words, when k is 1, cos of 0 is 1. Good. When k is 2, cos of pi is -1. When k is 3, cos of 2 pi is 1. So this one here is another way to generate. So just be careful of that. If you see, you can use sine and cos to generate 1 and -1. Yeah? In this way. Okay, so agreed? So this one will generate, if we like, this one will actually equal to, we'll have what, 1, -1, 1 and so on. How could we do it for sine? Does anyone want to have a guess about sine? How would we make that for sine? It'd have to be sine of, well we need it to generate 1, then we need it to generate 3, don't we? So could we go 2k or minus, yeah, so we could go basically what, 2k minus 1 pi on 2. So when k is 1, we end up with pi on 2. Sine of pi on 2 is 1. When k is 2, we end up with 3 on 2 pi, and so on. Again, this will generate 1, -1. Yeah? So just be careful. You'll see this. Now, 90% of the time you see this one. I rarely see these. But sometimes you do. Sometimes you'll see these in the past exam papers. Just be careful. They're just sign generators. They look complex, but really they're just generating either 1 or -1. So just watch out for those ones there. Yeah? So this will, of course, also generate 1 and -1 and 1. And there are probably other ones that I don't know about, but just off the top of my head I can't really think of right now. But they're the most common ones. Okay? Question is, Arthur, does this converge or diverge? Do you think it's more likely to converge? Let's just draw a picture of it, shall we? So if I was to draw an axis of what's actually happening here. So on this axis here I have n. Yeah, I have n here. I wish I had my red texture, but I don't. On this axis here I've got Sn. Okay? So, let's go here to my first term. My first term we jump straight up to 1, don't we? So here's my first term here, so I'm going to jump straight up to 1. There's 1 there. So here's my U1, which is 1. We go straight up to 1. Then what do? We subtract off. We subtract off for my second term. We have to go -1. So we come down here. I'll just put a little dash up here like so. And we come down to -1. So there's U2. Yeah. There is U2. And guess what? We're down here at a half. Agreed? So I've got 1 minus a half. And here's S2. Here's S1. Cool? Next what happens is we jump up to, we've got to now add a third. Well, who knows what that is, but let me just draw it for you. We now go up a third, which will be about there. Then what do? What do I have to do after that, ladies and gentlemen, is I've got to subtract 1/4, which is about this long. Do you think I am diverging or converging? In actual fact, we are converging. Yeah? In actual fact, we are converging to ln2. I'm not going to prove that for you, but that's actually what this series converges to. Yeah? The alternating series converges to that. I'm not going to necessarily prove that to you, but that's exactly what's actually happening here, is that there is convergence here. It is actually converging. So, if I was to formulate these dots, what we're actually getting is this. There's the first one. Here's the second one. Yeah? There's the third one. Here's the fourth one. The chance of this series. Now, what two things do you think this series needs? Clearly you can see, I think, this is going to get closer and closer to that, isn't it? Yeah? What two conditions do we need, therefore, for an alternating series to occur, do you think? If I've got an alternating series, what two conditions do I need? No? No? Vincent, what two conditions do you think I need? Notice what's happening. What do you think? This term here, can anyone just watch for a sec? Arthur? I think you can probably all see this here. Can someone please tell me what do you think is happening to this term here? What needs to be true for that term for it to converge? It must get smaller and smaller and smaller, agreed? Yeah? So what must it approach though? There's two things that must approach. That term needs to approach 0, doesn't it? This term here needs to get infinitely small for it to converge clearly, doesn't it? Yeah? If that term didn't get smaller, it's never going to converge. So the term must get smaller and smaller and smaller and approach 0. And the other thing is, Vincent, the other thing is this term needs to be smaller than that. Do you agree? This term needs to be smaller than that. This term needs to be smaller than that. So basically, the next term needs to be smaller than the previous term, forever. So how do I say that? Well, I say that by saying this. The first condition is what? U, K plus 1 must be less than UK. If we like. In other words, the absolute value of UK plus 1 must be less than the absolute value of UK. True? Each term must get smaller and smaller. And what else must happen? Not only must it get smaller and smaller and smaller, but it must get closer and closer to 0, not closer and closer to some other limit. If UK got closer and closer to 1, we'd just be adding and subtracting 1 each time, wouldn't we? So that's not good enough. So this condition is the first one. How could you say about that? It really must be decreasing, yeah? The absolute value of UK must be decreasing all the time, but in addition to that, the second condition for an alternating series test is this, that the limit as k approaches to infinity of UK must equal to 0. They are my two conditions for an alternating series. Now, how could I test this? How could I test it's decreasing? Two ways. How could I test that the series is decreasing? The absolute value of the series is decreasing. There are two ways. One is just to use an inequality. The other is to use differentiation and show that it's a decreasing function. Yeah, so the two main ways to show this, the two main ways to show it's decreasing, one is to use an inequality, which I'll show you in a sec, and the second way is to use differentiation. What do I mean by using differentiation? I mean really f dash k must be less than 0. So in other words, you formulate this into a function and you show that its derivative is always less than 0. Cool? Shall we do that in this test? So how would you do this test? How would I show that this here is converging? Well, let's go. So how do I show that's converging? So what we'll do is we'll show that, and then we'll do another example out of the book, show that the sum minus 1 k plus 1, 1 divided by k from 1 to infinity is converging. Load it up. How do I do that? First thing, what do I need to do? 1. Show that the absolute value of UK plus 1 is always less than the absolute value of UK. So how would I do that? Well, let's just use an inequality. The two ways. This is the easiest way. The most common way is just to form an inequality. Watch this. So I'm going to go k plus 1 is greater than k. K plus 1 is greater than k. Which means what? That 1 on k plus 1 is less than 1 on k. Therefore, what does this mean? Therefore, UK plus 1 is always less than UK. That's the most obvious way to do it. Agreed? The k plus 1 term is always less than the kth term. What's the other way that you would do it? You could use differentiation. So this is the most common one. The other way is to go, let's let f of x equal to 1 divided by x. Agreed? So therefore f dash x equals to minus 1 on x squared. Now because x is greater than 0, f dash x will always be less than 0. Yeah? Therefore we have a decreasing function. Yeah? So therefore it's decreasing. Cool. Okay, there's the first test. What's the second test, everyone? What do I need to do? The second test is to show that the limit as k approaches to infinity of UK equals to 0. So I've got to show that. So let's do that, shall we? So, and this is the absolute value of UK, by the way. I'm not interested in the sign generator. Okay, so let's do that. So we've got the limit as k approaches infinity, of course, of 1 on k. Guess what? That equals to 0. Now there's your conclusion. What's my conclusion? Therefore, this alternating series will converge. So then of course you just need a conclusion. Therefore, so here's my conclusion. I'll go get a red texter, I haven't got one. So the conclusion is, therefore, alternating series will converge. Okay, take that down and let's just do one out of the textbook. Say one or two. How much time have I got left, Brian? 4 minutes. No, I'm not going to get another one down. Take that down and I'll see you all this afternoon. We'll do 2 out of the book. I don't think we're going to get onto this ratio test today, but if we could just get the alternating test done today, I'll be happy. Maybe we can just keep going a little bit longer today until we finish this and at least look at the ratio test, because tomorrow's class is quite long as well. I don't know. But then we'll finish all of chapter 3. Okay. See you all later. I don't think we'll have time to move on. So can I see you all sharp, 2:30?